This is section 2.5. This is 3D vectors, three-dimensional vectors. And we're going to start just by talking about the 3D axes. And the 3D axes, three-dimensional axes, are x, y, and z, x-axis, y-axis, z-axis. And it's very important that they be oriented in this way. This is based on the right-handed coordinate system, and you can read about that a little more in the textbook if you wish. But it's if you try to understand it, if you put your hand on an axis, the fingers are on the x-axis, the hand and forearm is on the y-axis, and then your thumb will be pointed up in the z-axis. If you try this with your left hand, then you'll get a little mixed up. So it's very important to do the right-handed coordinate system. And the XY plane, I'm just kind of sketch it here, is generally on the horizontal plane, on like a table. So if we use this kind of convention, then we won't get mixed up, and the signs, SIGNs of your answers should be correct. Well, I like to use this PVC pipe arrangement to show what the x-axes might be, but here's, so you can see the x, the y, and the z, and these are going to be positive in each one of these directions. There's going to be a plane made by the XY axis in this way. So it's going to be with the horizontal most of the time in most of our configurations. There may be some negative axes, which we'll just want to place these rulers here so you can see that this would be the negative x-axis, the negative y-axis. And the forces can be described in any one of these four quadrants, if you will. There's going to be a quadrant here and here. This one would have a component that's positive in the x-axis, positive in the y-axis, and positive in the z-axis. One back here would be in the negative x-axis, negative x-axis, negative y-axis, but still in the positive z-axis. So you can see how forces might be in any one of these quadrants and be described. Now we have talked about the two-dimensional coordinate system, and here's just some things that we talked about before, that if you have an angle theta, you'll have a force in the x direction, a force in the y direction. We know that we can express that as a Cartesian vector. We know cosines and sines of that angle theta. If, however, one of the angles, or the angle is expressed as an angle phi, then you'll have the cosine of phi in that, or the cosine of theta in that direction, and the cosine of phi in that direction. And that's what this one is all about. Cosine theta in the I direction, cosine phi in the j direction. We've talked about how to find the magnitude by summing the square root of the sum of the squares. And here's a trig identity, which may come in handy occasionally, where cosine squared theta plus cosine squared phi equals 1. And then we've also talked about how to find resultants, two-dimensional resultants, again, where there's the resultant in the x direction would be the sum of the forces in the x direction. The resultant in the y direction would be the sum of the forces in the y direction. Now what we've got in 3D is some analogous understanding. But here, instead of having theta and phi, we're going to call the angle that the force, this is the force, the angle that the force makes with the positive x-axis, we're going to call that alpha. The force that it makes with the positive y-axis, or the j-axis, beta, and the angle that it makes with the positive z-axis, gamma. With that, then there are some analogous equations which can be applied. We know that the forces are going to be the sum of the forces in the x, y, and z. And here's where the cosines come in. The force, the main force is the sum of cosine alpha in the I direction, cosine beta in the j direction, and f cosine gamma in the k direction. So the magnitude will be found in a similar way. And then here's a trig identity, which allows us to find missing angles if two of them are given. Just like we had back here, cosine theta is equal to the force in the x direction over the magnitude of the force. Cosine alpha, cosine beta, and cosine gamma can be found in a similar way, as well as the magnitude, and understanding that the resultants are the sum of the forces in the x, the y, and the z. Well, let's use this understanding to come up with a vector description, a Cartesian description of this force. You can see that it is aiming backwards in the x direction. In other words, there's a component in the negative x direction. There's a component in the negative y direction, but the z component is positive. So let's look at the angles that are given here. It's given that this angle right there with the positive z-axis is 60 degrees. So this is angle gamma. It's given also that this is angle 60 degrees. However, it's made with the negative x-axis. So if we want to find angle alpha, we need to look to see what it is with the positive x-axis. So we'll call this positive angle alpha. The angle that this force makes with the j-axis or the y-axis will be in this direction, and we'll call this angle beta. Okay, so let's just define what we know. Angle alpha is going to be 180 degrees minus that 60, so alpha is, by observation, is 120 degrees. Gamma, by observation, is positive 60 degrees. Beta is something we don't know, so let's use our trig identity, see if we can come up with that. So cosine squared, need the cos squared alpha, and that's going to be 120 degrees, plus cos squared beta, which is our unknown, plus cos squared gamma, which is 120. Gamma is 60 degrees. Sorry about that. 60 degrees. And that's going to be equal to 1. All right, we can simplify this. I can take that cosine squared 120 degrees, that is 0.25, plus cos squared beta. Cosine squared 60 degrees is also 0.25 equals 1. Then you can solve this for cos squared beta is equal to 0.5. Now here, maybe there's more than one way of doing this, but I'm going to take the square root of both sides here. So I'm going to say this is cosine of beta is equal to the square root of 0.5. Then I can find beta is equal to the inverse cosine of the square root of 0.5. And that has two values. It has 45 degrees and 135 degrees. So when you solve these things, you're going to have to make sure that you solve for all of the possible angles associated with this. So then we look at our picture and say, what is the valid answer? Well, it probably makes more sense if you just look at the picture, that because this force is kind of going in the negative y direction, that it makes sense that angle beta is greater than 45 degrees. So the correct answer would be 135 degrees. Beta is equal to 135 degrees. All right, from there we can solve this little problem. All right, what we're looking for is the Cartesian coordinate or Cartesian description of this force. The magnitude is given, so I'm just going to say F is equal to 500, which is the magnitude, times the cosine of alpha in the I direction, plus cosine of beta in the j direction, plus cos gamma in the k direction. Using the angles that we've previously determined, I'm just going to write the answer down. I'm going to call that F is equal to negative 250 I, negative 353 j, positive 250 k. And that's our Cartesian description of that force. Now, another method of understanding how to describe 3D forces, it's not really another method, it's just when different information is given to you, then you use this method, and I'll call this the F prime method. But what we have here is we have a force going up, and we have some angles that are defined here. And the way we interpret this drawing, or interpret this is the XY plane. So this is the XY negative plane. What it says is that the projection, or the value of x, or the value of this force on the xy plane, is the cosine of the magnitude in this direction. So we'll call this the F prime point right there. Then f of x is in this direction, and f of y is in this direction, then fz is in this direction. Once we find the value of f on the xy plane, then we'll say that fx is equal to the cosine of 45. In other words, here's the 45-degree angle. The sine component will be there, so that will be the fy will be the sine of 45. Fx again is the cosine of 45. Then fz is going to be the sine of 60. So this would be the cosine in that direction, and the sine of 60 would be there. So we'll just write those down. We're going to say that fx, or f prime, is equal to f cos 60. Fx will be equal to f prime cos 45. Fy is equal to f prime sine 45. And then fz would be equal to f, not f prime now, because we have that whole thing. That's going to be equal to the sine of 60. So I hope you can see all of those components when you have it expressed like that. So let's use that to solve another one. We have this force. It's kind of going up at an angle. We have an angle that it makes with the xy plane, which looks like that, and it's 45-degree angle with the xy plane. So I'm going to say that f prime, let's go ahead and label f prime here. F prime is kind of the projection of the force onto the xy plane, and that would be the magnitude, which is 50, times the cosine of 45. So f prime is f cosine 45. That's given there. We have some forces in the x direction now. I'll say that there's going to be a component in the x direction. I'm going to draw this going backwards right there. Another way, actually it might be easier to look at this from the y direction first. So in the y direction there's going to be that component, which would be fy. And using the triangle method, I'll put fx looking like that. That might be the easiest way of describing it. Then fz would be going up like this. Again, using the triangle method rather than the parallelogram method where all the forces come from the tail of that force. So let's just look at them then. Fy is going to be the 4/5 component, because that's going in that direction, times f prime. Fx would be the 3/5, again 3/5 component, times f prime. Fz is going to be the sine of this magnitude of the total force times 45. And then you can also find alpha, beta, and gamma using our previous rules, and then you can write the force as a Cartesian vector. Another thing we can do with the f prime method is find resultants, or we can use what we know already to find resultants if we can adequately express the descriptions, the Cartesian descriptions of the forces. So using the f prime method, we'll just call this f prime of 1 right there. So this is the f prime right there. We can call there's a component in the x direction. That'd be f1x. This would be in the y direction, f1y. And this would be in the z direction, f1z. Alright, you can follow the work here to find out how to describe those three pieces. To find the resultant of these forces, then look at F2. F2 is only going in the negative z direction, negative k. So that would be negative 130k. To find the resultant, just write the vector descriptions, the Cartesian descriptions of the forces, and add them together. F1 plus F2 is resultant, and here is the vector description of that resultant. Okay, so now I'd like you to pause the video and see if you can come up with the resultant of these two forces. the first force, F1, you can see that it is in the Y, the YZ plane, if you will. There's a plane made YZ. It's going to be negative in the Z, positive in the Y, and there is no component in the x-axis. For the F2, you can see that there's an alpha, beta, and a gamma given. So just find out the Cartesian descriptions, add them together. And after you get done with that work, here is the solution. The resultant is going to be equal to F1 plus F2. F1, you'll have a 7/25 component in the positive J. 24/25 times 50 in the negative K. F2 be cosine alpha, which would be cosine 60 in the I direction, cosine 135 positive in the J direction, cosine 60 in the K direction, and then you just add them together. You can also sketch the resultant in a 3D axis if you want, or if it's required. And so in this case it had 90 in the positive I, negative 113 in the J direction, positive 42 in the K direction, and that would be the resultant.